everyone, welcome to the Deep Dive, your ultimate shortcut to effortlessly being well-informed. Today we're really plunging into something that's, well, it's becoming woven into the fabric of our lives, literally minute by minute. The Internet of Things, or IoT, I mean, just think about it. That smart thermostat adjusting your home's temperature before you even arrive.
Right.
Or the complex network of sensors managing traffic in a smart city, or even those systems keeping industrial machinery humming.
Yeah, they're everywhere now.
Our daily routines, our businesses, critical infrastructure, it's all increasingly dependent on these connected devices. They're truly shaping our existence, often invisibly,
Until something goes wrong. Exactly.
Precisely.
And with this growing dependence, this omnipresence almost, comes a really fundamental challenge. The absolute need for resilience.
Non-negotiable, you mean?
Absolutely non-negotiable. It's not a nice to have anymore.
Yeah.
Continuous operation of these IoT systems, from the tiniest sensor up to, huge industrial controls, it's become a necessity. The stakes are just incredibly high. We're talking economic stability, public safety, even human lives.
Yeah.
The world just can't afford these systems to fail often or for long.
And failure, unfortunately, is a very real possibility.
Increasingly complex, too, right?
Yeah.
We're facing this constantly evolving threat landscape.
That's right. It's diverse.
Yeah, everything from, the sheer force of natural disasters, think floods taking out sensors, heat waves frying electronics.
Storms ripping through comms infrastructure.
Exactly. Physical attacks from the environment itself.
Wow.
But then, of course, there are the, let's say, more insidious digital assaults.
The cyber attacks.
Right. Massive botnets like we've seen using insecure devices to launch attacks,
Yeah.
or ransomware hitting critical systems.
Holding operations hostage. Yeah, it's nasty stuff.
And we can't forget the maybe more mundane stuff like software bugs hiding in the code or just human error.
Oh, absolutely. A simple misconfiguration can cause chaos. It happens. So the complexity, the variety, the severity of these threats, it's all increasing, which makes resilience more urgent than ever.
So yeah, our mission today is to really do a deep dive into what building resilient IoT ecosystems truly means. We need to unpack how we design these systems not just to withstand disruptions, but maybe more importantly.
How they recover quickly and efficiently.
Exactly. With speed, efficiency, sometimes without anyone even needing to step in. It's not about hoping for the best.
It's about preparing for the worst, systematically.
Precisely.
And we'll do that by looking at real-world examples, what worked, what didn't. We'll draw on expert advice, emerging trends.
The goal is really to help you, our listeners, understand how to design for resilience from the start, test for failures effectively, and, lead organizations towards a more secure, stable IoT future.
Because this isn't just about tech fixes, is it? It sounds like a fundamental shift in how we approach connected systems entirely.
It really is a holistic shift,
Oh.
from the microchip right up to the cloud. Hashtag understanding resilience in IoT.
Okay, so let's kick things off by laying a clear foundation. What exactly do we mean by resilience in the IoT context? It gets thrown around a lot, but what's the core idea here?
Good question. Perfect place to start. So, at its core, resilience in IoT is about a system's ability to, first, maintain functionality even when things are going wrong.
Okay, keep working under pressure.
Right. And second, just as vital, to recover quickly from any kind of disruption.
And disruptions could be anything.
Pretty much anything. Digital, like a cyber attack trying to flood the network, or physical, a power outage, extreme weather, physical damage. The key thing is, resilience isn't just prevention. It's about enduring the unexpected and bouncing back fast.
Bouncing back without losing service or data.
Or operational capability, exactly. That's the goal.
Now, many listeners might know about traditional IT resilience, data centers, redundant servers. But IoT feels different. Why is that?
It is fundamentally different.
Enterprise IT often lives in controlled environments, right? Climate control, stable power, fast networks.
Right.
But IoT, it's out there in the wild sometimes.
Exactly. That's the key difference. IoT devices might be running on tiny batteries for years.
Deployed in harsh conditions.
With spotty or unreliable connectivity. Built with specific, often resource-constrained hardware. These aren't powerful servers in a rack.
They're often tiny devices scattered everywhere. So how does that change the game for resilience?
Oh, you've hit the nail on the head. That's the core architectural challenge. Because IoT systems are so distributed, often covering huge areas with thousands, maybe millions of endpoints.
And they're made of these resource-constrained devices.
They are just inherently more prone to disruptions than a big, centralized IT system. Each device, each sensor, each gateway is a potential point of failure.
So the attack surface is massive, and it's spread out over unpredictable terrain.
Precisely. Unlike a data center where you might double up on a few key servers, here you have countless potential weak spots exposed to all sorts of variables. Traditional strategies focusing on central points just don't cut it.
So you need a different approach, something embracing decentralization.
Exactly. Decentralization and local autonomy become critical because these systems operate right at the edge, often in tough conditions.
So given that inherent fragility, maybe what does always on really mean for IoT? And why is it so critical when these things are plugged into our physical world? Power grids, healthcare.
That's a crucial point. For IoT, always on often means real-time interaction with the physical world. Downtime can have immediate, tangible, sometimes severe consequences.
So reliability and fault tolerance are key.
They're the absolute cornerstones. Reliability means the system just works as expected consistently over time.
It does its job.
Right. Fault tolerance means it can keep operating correctly even if parts of it fail. It's about having that built-in ability to detect errors, recover gracefully without bringing the whole service down.
Designing against single points of failure, making sure there are alternative paths.
Exactly. That's how you engineer for an always available system. Designing for robustness, even if some parts aren't working perfectly.
And when those cornerstones aren't solid, the consequences. They can be pretty stark, can't they? Let's move beyond theory. What are some real-world examples of significant failures?
Oh, definitely. Let's take smart city infrastructure. Imagine traffic lights failing across a major city during rush hour.
Chaos. Absolute gridlock. Increased accidents.
Undeniably. Or think about public safety sensors, air quality, environmental hazards suddenly going dark. The city's blind, can't monitor critical conditions, can't respond effectively to emergencies. Puts people at risk.
The impact is immediate.
Instant and severe. Then there's industrial downtime. In modern manufacturing, just one IoT sensor failing, maybe monitoring temperature or pressure.
Could bring the whole production line to a grinding halt.
Exactly. And that's not just inconvenient. It's huge economic losses, missed targets, supply chain delays, massive operational impact.
And energy grids. Smart meters failing.
That can impede load balancing, potentially leading to brownouts, even blackouts.
Yeah.
The financial and societal costs are staggering.
Wow. But then there's the really critical area. Medical devices.
This is where it gets incredibly serious. And the ethical stakes are highest. Think about IoT pacemakers, glucose monitors, insulin pumps, remote patient monitoring.
Right. Devices people rely on for their health, their lives.
A malfunction, or worse, a cyber attack on one of these devices, or the network they use, it can directly impact human lives. Patient safety is literally on the line.
So the need for resilience there is almost absolute. Multiple layers of redundancy, fail-safes.
An obsessive focus, really, because the consequence of failure can be irreversible. It's not abstract, it's deeply human.
So when you look at this invisible infrastructure running things, it needs to be as robust as a physical bridge, maybe even more so. You can't just send out a repair crew easily for software issues.
That's a great analogy.
And to understand that robustness, to trust it, we need ways to measure it, don't we? Metrics.
Precisely. We absolutely need quantitative measures. One key metric is MTTR, mean time to recovery.
Okay, how long it takes to fix things after they break.
Essentially, yes, the average time from failure detection to full restoration. Obviously, a lower MTTR means greater resilience. It shows the system can bounce back quickly.
Minimize the disruption. Got it. What else?
Another crucial one is availability percent. Pretty straightforward, the percentage of time the system is up and running over a given period.
Like 5 nines availability? 99.999%.
Exactly. That's a common target for critical services, meaning just a few minutes of downtime per year. It quantifies how often the service is actually working as intended. Achieving higher nines usually needs serious investment in redundancy. Okay.
And the third one?
Failover response time. This measures how fast the system can detect a primary component failure and switch to a backup, automatically, without human intervention.
Seamless switching.
Ideally, yes. For critical, real-time applications industrial control, autonomous systems' rapid failover is paramount. It ensures continuous operation, prevents disruption, keeps the service seemingly unbroken.
So we have MTTR, availability, failover time. But how do these numbers translate for users? What's the tangible benefit when these numbers are good?
It translates to trust and continuity. For the user, it means the traffic light works, the factory keeps running, the medical monitor doesn't miss a beat. It's assurance.
And for organizations,
Minimize losses, sustain productivity, protected reputation, and crucially, enhanced user trust. When your systems are resilient, you're not just preventing problems, you're building a foundation of reliability. You shift from reactive panic to proactive stability, hashtag T-threats to IoT resilience.
okay, that leads us right into the thick of it. Understanding what you're up against. Let's unpack the biggest risks to IoT resilience today. It's a moving target, isn't it?
Absolutely. Constantly changing. And the first front line, maybe the most dynamic, is cybersecurity. We're seeing increasingly sophisticated attacks targeting IoT specifically, exploiting their unique weaknesses.
Like botnets. I remember Mirai.
Mirai is a huge wake-up call. It harnessed hundreds of thousands of insecure consumer devices, webcams, routers.
Turn them into a zombie army.
Pretty much. Use them to launch massive DDoS attacks, taking major sites offline. It really highlighted the danger of devices shipped with default passwords, left unpatched. The scale was terrifying.
And it's evolved since then.
Oh, yes. A more recent, really chilling development is ransomware targeting IoT infrastructure. Not just your laptop, but the operational technology, the OT, that controls physical processes.
So locking down factories, energy grids, hospitals.
Exactly. Encrypting or disabling critical OT systems, demanding payment. The disruption can be devastating, forcing horrible choices between paying up or facing catastrophic downtime.
Wow. And what about the devices themselves? Firmware vulnerabilities.
That's a persistent, almost hidden danger. Insecure firmware, the low-level software of the device, if it's outdated, poorly secured, never patched, it's a wide-open door for attackers.
Because devices get deployed and forgotten.
Often, yes. Especially consumer devices or those in remote locations. Attackers can gain control, steal data, or add the device to a botnet. It's a fundamental flaw many manufacturers still struggle with across the product lifecycle.
I can see how the scale and constraints of IoT plus inconsistent security creates a perfect storm for attackers. But it's not just digital threats, is it? The physical world bites back too.
You're absolutely right. Environmental factors are huge. Natural disasters, floods, short-circuiting devices, intense heat waves causing failures.
Especially with devices often deployed outdoors or in harsh conditions.
Exactly. Severe storms damaging antennas, cutting power, fires just destroying infrastructure. These events directly impact sensor networks, edge devices.
Taking out the eyes and ears of the system.
Precisely. If your soil moisture sensors get washed away or air quality monitors melt, you lose data, automated systems can't make decisions, the system fails. It's a massive challenge when devices are meant to be in these environments.
So toughest digital defenses don't matter if the hardware is underwater or on fire.
Doesn't matter at all.
And then there are the threats from within. The ones we cause ourselves.
Right. Human error and software bugs. Even in automated systems, the human element is significant. Simple configuration mistakes, for example.
Not malicious, just
No.
an error.
Awesome, yeah. A typo in an IP address, a wrong setting applied during an update. But it can ripple outwards.
Yeah.
Imagine one wrong parameter taking down HVAC in a smart building.
Crippling the whole system from one mistake.
Wow. So systems need to be robust enough to catch or mitigate those inevitable slip-ups?
What about updates? They're meant to help, right?
Usually. But firmware updates gone wrong are a nightmare. A faulty update can brick devices, making them useless, or accidentally introduce new vulnerabilities.
Ouch, so you need rollback plans.
Absolutely critical. And then there's the constant danger of unpatched vulnerabilities, known flaws that just haven't been fixed on deployed devices, easy targets for attackers who are actively looking for them. It's a race.
It really highlights the need for robust processes, automation, relentless testing, especially at scale.
Couldn't agree more. And the threats don't even stop at your own doorstep. Supply chain risks add another layer.
Because systems rely on so many third parties. Hardware, software, cloud services.
Exactly. Your resilience is tied to theirs. A flaw in a chip from one supplier, a big cloud outage. It can hit you hard, even if it's completely outside your direct control.
Creating downstream effects, like a component shortage, delaying repairs.
Or a cloud outage making your devices inert because the back-end processing is down. Even if your devices are fine, the system stops working. These disruptions can cascade rapidly.
It's fascinating. Resilience means looking way beyond your own operations, doesn't it? To the whole ecosystem.
It truly does. A holistic view is essential. #tag design principles for resilient systems.
Okay, understanding those threats is step one, but real resilience, as you said, starts way earlier, at the design phase. You can't just tack it on later.
Precisely. It has to be a fundamental design principle baked in from the beginning, not an afterthought. It saves so much pain later on.
So what are some of those core principles?
Well, one cornerstone is modular architecture, breaking down large, complex systems into smaller, independent modules.
Decoupling components.
Exactly. Think microservices, but for IoT. From the device firmware right up to the cloud components. By doing this, you limit the blast radius if something fails.
Ah, so if one module fails, it doesn't take the whole system down with it. Like bulkheads on a ship.
Perfect analogy. It isolates the failure, contains the problem, and that makes recovery much faster. You can fix or replace that one module without taking the entire ecosystem offline.
Faster MTTR, continuous operation for the rest. Makes sense.
Another critical principle is redundancy. Not just one backup, but multiple sensors, devices, communication paths doing similar tasks or ready to take over.
Duplicate components, alternative routes for data.
Right. If one temperature sensor fails, maybe two others are still working fine, providing the needed data without interruption.
So that provides that critical failover coverage. If a primary fails, a backup takes over seamlessly.
That's the idea. It's the built-in plan B.
Yep.
Essential, especially for remote devices where physical intervention is tough. Then we have fail-safe mechanisms, designing systems to default to a safe state if there's a major failure.
Prioritizing safety over full function.
Absolutely. Especially crucial for industrial controls, smart transport, medical devices, where failure could be dangerous. Caution over chaos.
Does that include devices working even if they lose connection? That local control idea.
Yes, that's paramount. Devices need to function autonomously, maybe with reduced features if central communication is lost.
Like smart lights defaulting to on if the controller fails, not plunging a building into darkness.
Exactly. Or a medical device maintaining basic monitoring. Local intelligence ensures safety and basic function even during an outage. And underpinning all of this must be secure by design. Security isn't a layer you add, it's embedded from the start. And the hardware, firmware, protocols, cloud integration.
Building security in, not bolting it on.
Correct. Secure boot, hardware root of trust, strong authentication from day one.
And how does that proactive security directly boost resilience?
Simple. It prevents downtime caused by attacks in the first place. A system that's inherently harder to compromise is less likely to suffer unexpected outages due to malicious activity. Security is resilience in that sense, building a fortress. Finally, a really powerful principle is automated recovery, self-healing systems.
Systems that fix themselves. How does that work?
Through smart monitoring, pre-programmed recovery scripts, sometimes AI. Think restartable services. If a process crashes, the system automatically detects and restarts it.
Minimizing human intervention and downtime.
Exactly. Or automated configuration management, reverting to a known good state. For IoT, maybe an edge gateway detects a bad sensor, isolates it, reboots it, or rolls back its firmware automatically.
Improving MTTR, boosting availability, making the system more robust with less manual effort.
Precisely. Designing for autonomy and intelligent self-correction. Hashtag real-world case studies.
Seeing these principles in action really drives it home. Let's look at some real-world examples, successes, and, well, failures to learn from.
Absolutely. First, a success story. A smart grid operator. They managed a rapid service restoration after a major blackout. It wasn't luck. It was their proactive resilience planning.
What did they do? What saved the day?
Two key things. First, sophisticated predictive maintenance. Using analytics on sensor data from the grid to spot potential equipment failures before they happened, allowing preventative repairs.
Okay, fixing things before they break. Smart.
And second, autonomous rerouting. When a fault occurred, the system automatically analyzed the network and rerouted power through alternative paths, bypassing the fault.
So the system itself adapted and self-healed, restoring power incredibly fast.
Often in minutes, not hours. Minimal human intervention needed in the heat of the moment.
Impressive. What about healthcare?
Another great success. A hospital maintained all its life-critical monitoring systems during a major global cyber attack. No interruption at all.
Wow. How? Especially when others were hit hard.
A layered approach. Crucially, air-gapped systems for the most critical devices physically isolated. No direct connection to the main network or internet.
So the attack just couldn't reach them.
Correct. And for any necessary communication, they used robust encrypted protocols, often on private networks, ensuring data integrity and privacy even if external comms were hit.
It really shows the power of isolation and strong encryption in high-stakes areas. What can we learn from systems where downtime could be fatal?
It underscores that resilience there isn't just vital, it's an ethical imperative.
Okay, now for a cautionary tale. A failure to learn from.
Yes, consider a major recall by a consumer wearable company. It highlights that poor resilience has broad impacts, even for non-critical devices.
What happened there? What caused the recall?
A faulty firmware update. Pushed over the air, it bricked thousands, maybe millions of devices, rendered them completely unusable.
Ouch. Dead devices, angry customers.
A PR nightmare, huge financial costs. It screams the need for robust rollback systems. A plan B for updates. The ability to quickly revert to a stable version if an update fails.
Because updates can go wrong.
They absolutely can. This case shows that even for consumer gadgets, the cost of poor resilience recalls, reputational damage, lost trust, lost revenue, is immense.
These examples really hammer home that design is only half the story. You absolutely have to test resilience.
Rigorously and continuously. Which brings us to testing. #tag testing for resilience.
Right. Designing for resilience is one thing, but you have to validate it through testing. Pushing the limits, right?
Exactly. It's not enough to hope it works. You need proof. A key technique is stress testing.
This isn't just checking basic function, it's about overload.
Precisely. Intentionally hitting devices, networks, cloud components with excessive data, connections, or tasks, pushing them way beyond normal operating limits.
Why? What's the goal of breaking things intentionally?
To find the breaking points, the bottlenecks, the weird behaviors before they happen in the real world. Identify hidden limits, see how it handles extreme load. Find the cracks before the whole thing collapses.
Okay. And building on that, disaster simulation.
Yes. Disaster simulations or chaos engineering. Proactively emulating real-world disruptions in a controlled way.
Like simulating cyber attacks, power cuts, network problems.
All of the above.
Yeah.
Intentionally injecting latency, packet loss, simulating hardware failures.
And there are tools for this, like Chaos Monkey, Gremlin.
Exactly. Tools designed to intentionally inject failures, shut down servers randomly, spike CPU, mess with the network. It's like fire drills for your infrastructure.
Yeah.
Forces you to find weak spots and validate recovery plans. Build confidence through controlled chaos.
Makes sense. What about getting insights from actual users?
Crucial. That's user-in-the-loop testing, going beyond labs and scripts, gathering insights from device logs, but also direct user feedback.
Because labs can't replicate the real world perfectly.
Never. Users interact in unpredictable ways, in varied environments. Their feedback highlights subtle, edge case failures you'd miss otherwise.
Yeah.
Issues that only emerge under specific real-world conditions. Getting that human perspective is invaluable.
Okay. And finally, regression testing. Rollback plans.
Absolutely vital. Regression tests ensure that new updates or changes don't accidentally break something else or reintroduce old bugs. Every release needs thorough testing against the baseline.
Prevent unintended consequences. And the rollback plans.
Hand in hand. As we saw with the wearable company, updates do go wrong. A clear, tested rollback plan lets you quickly revert to a stable version if needed. Minimize downtime, mitigate damage.
So the question really is, are you prepared for when things inevitably go wrong? Or just hoping they won't? Resilience means having that safety net.
Exactly. That clear path back to stability. #the role of edge computing in resilience.
That idea of local control and fast recovery leads us neatly to a really key architectural shift. Edge computing. Let's unpack how this helps with IoT resilience.
Right. Edge computing is fundamentally about decentralizing processing. Instead of sending all data back to a central cloud.
You bring the computing closer to the devices, to the edge.
Exactly. Logic, storage, even AI capabilities move closer to where the data is generated. And this has profound benefits for resilience, especially in critical, real-time situations.
Okay, like what? What are the key advantages?
Well, first, significantly reduced latency. Processing data locally eliminates that round-trip delay to the cloud and back.
Which means faster response times in emergencies, crucial for autonomous vehicles or industrial controls.
Absolutely critical. Where milliseconds matter, that fraction of a second saved by local processing can prevent disaster. It provides instant, localized intelligence.
Makes sense.
What else? Autonomy during disconnection. This is huge for IoT. Because edge devices can process data and make decisions locally, they can keep working even if the internet connection to the cloud drops.
So a smart factory keeps running even if its internet goes down. Or a smart building maintains security.
Precisely. Local intelligence ensures continuity even during network outages, prevents total paralysis. It's vital in remote areas or places with unreliable connectivity. Edge computing also enables localized failover. Think mesh networks, where edge nodes are interconnected.
So if one device or hub fails,
Others nearby can automatically take over its tasks, detect the failure, step in seamlessly.
Like in a smart lighting grid, adjacent lampposts pick up the slack if one controller fails.
Exactly. They can reroute data, maybe even assume some of its functions temporarily. This local redundancy maintains network integrity, prevents a single failure cascading. The system self-heals locally, incredibly robust. And finally, Edge can improve security at the edge. By processing sensitive data locally, you reduce the attack surface. Less data traveling to the cloud means fewer interception opportunities.
Limiting the potential blast radius of an attack.
Right, if one edge node is breached, the impact is contained locally, rather than compromising the whole central system. It distributes risk.
It's fascinating how distributing processing improves speed, autonomy, and security. It's not just one benefit.
It really tackles many of the core IoT constraints, head-on resource limits, connectivity issues. It makes devices more self-sufficient, responsive, and robust, a powerful enabler of true resilience. Hashtag tech collaboration between developers and management.
Okay, we've covered technologies like edge, design principles like modularity, but it strikes me that technology alone isn't enough. True resilience feels like it needs to be an organizational mindset.
You're absolutely right. It requires deep synergy between the tech teams and leadership. It's not just a tech problem, it's a business imperative.
So what's management's role here, beyond just approving budgets?
Well, approving budgets for resilience is crucial, seeing it as an investment, not just a cost. For design, redundancy, testing, maintenance.
But it's more than money, right?
Oh, definitely.
Yeah.
Leadership needs to actively plan for downtime. Understand what will happen, develop practiced incident response plans, clear communication protocols.
And fully support the response teams. Give them resources, authority, training.
Exactly. Seeing resilience as core to operations, reputation, and revenue, not just a cost center. And bridging the gaps between departments is essential. Regular syncs between product owners, developers, and operations teams.
Why is that so important?
To get everyone on the same page. Share insights, understand constraints and priorities. Align on risk appetite.
Because different teams might see risk differently.
Absolutely. Collaboration helps everyone understand and agree on acceptable risk levels and the measures taken to mitigate them. Avoids surprises and ensures a unified approach. And to track this, you need metrics that matter for resilience. Specific KPIs everyone agrees on, like clear downtime thresholds.
Defining acceptable unavailability for different services.
Right. A smart light can tolerate more downtime than a medical monitor. Also, tracking alerting responsiveness, how quickly does the system or team react?
Speed matters. And learning from incidents.
Crucial. Incident postmortems. After every disruption, a thorough, blameless analysis. What happened? Why? How do we prevent it next time? Turn every failure into a learning opportunity. Drives continuous improvement.
It raises that question again. Are your teams speaking the same language about resilience? Is it a shared priority?
And finally, a resilient organization practices. Training and drills. Cross-team simulations of failure scenarios.
Not just talking about it, but actually doing it, like fire drills.
Exactly. Hands-on simulations. Practicing roles, coordination, communication during a controlled crisis. Builds muscle memory.
Like that symphony analogy, everyone knowing their part when the unexpected happens.
It transforms potential chaos into a well-orchestrated recovery. Ensures that when the real disruption hits, the organization is proficient, not just prepared. Minimizes impact, maximizes uptime. Hashtag Capware case summary and key takeaways.
All right, as we wrap up this deep dive, let's quickly recap. We've seen IoT systems face unique challenges demanding resilience beyond traditional IT.
And the threat landscape is complex. Cyber attacks like botnets and ransomware, hardware failures, natural disasters, human error, supply chain risks, they're all significant.
But resilience starts at the design level, right? Baking it in with modularity, failover, local autonomy, and secure by design principles.
Absolutely. But design isn't enough. Rigorous testing, simulating failure, pushing limits, that's just as critical. You have to validate the design under pressure.
And we highlighted key enablers. Edge computing for decentralization and local robustness.
And that crucial interdepartmental collaboration, making resilience an organizational mindset, not just a tech task.
Which brings us to the final key takeaway.
Yes, the big one. Resilience isn't a checkbox. It's not a one-and-done task. It's a continuous, evolving discipline. It requires constant vigilance, adaptation, investment.
Because the threats change, technology changes.
Exactly. It's a marathon, not a sprint. An ongoing commitment.
So by taking that proactive, strategic approach, integrating resilience deeply, testing rigorously, leveraging architectures like Edge, fostering collaboration, organizations can protect their investments, enhance trust, and stay operational.
Even when disruptions inevitably occur, that's the goal. Hashtag tag outro.
So, as we rely more and more on these invisible connected systems everywhere, what does true resilience mean for your peace of mind, for your business continuity, even for your smart home?
Well, consider this. In a world where everything's connected, true strength isn't about avoiding disruption that's impossible. It's about the ability to adapt, absorb shock, and recover quickly. So, what small step can you take today towards resilience?
Like updating firmware, asking about resilience in a new system, talking about incident response.
Exactly. Any small step. It all adds up to greater stability in the long run.
That's a great thought to leave everyone with. A practical call to action. We really encourage you to keep exploring these topics, maybe look into specific frameworks or dive deeper into case studies. Thank you so much for joining us on this deep dive into IoT resilience. We hope it's left you feeling informed and hopefully a bit more empowered.